Okay, so this is a continuation of the first example of class 13, where I walk through the instantaneous center of rotation for this. I get the velocity of this, and in this fourth version, or this fourth part of the example, I go through the ICR. So we got the solution via the vector math, and we found to be 3.894 at the 74.37 degrees. Also, the midpoint step that we got was that the angular velocity was 0.4138. We also did it in 3-diagram method, and we were able to get the same thing. And then we were able to use velocity triangles, which is really just another way of approaching the 3-diagram method to be able to get the same result. So now we go to the instantaneous center of rotation. The difficult part here is finding the location of the ICR, and that's not actually all that difficult. But then also finding the dimensions. And the first part of this is easy. It's this last one that's kind of difficult. So let me go back to the original one and remember, just to remind you, the method of the ICR. What you want to do is draw lines through the velocities, right? So the velocity of A is going to be in that direction. So we want to draw lines that are perpendicular to them, to both of these velocities. So this one turns out to be nice and convenient, is horizontal, and this one's convenient. So where they merge right there is the ICR. So it is essentially going to be rotating about that ICR. The difficult part here is that I ask for the velocity of c, so we need to get a line from the ICR and draw it to c, and then the velocity of c is going to be perpendicular to that line that we drew through the ICR. All right. So let's see, you got to scroll through these and come down, and boom. So I've drawn all that out. That's how I found these. And if I want to find that length, the RC with respect to ICR, I have to break this thing down a little bit further into the geometry. And you could see that what I did here was just to extend this line out and come down to here. Because I know the length here and I know the angle, I'm able to get this distance right here. And I also have this distance right here, and then I also know this distance. So I'm able to get what this is. But that might not be obvious, except that I just showed you how to do it. But you have to think your way through the geometry and pick it apart to try to get that. So from the geometry, I made a sketch, and I was able to find, well, first off, I know this ICR, the A with respect to the ICR is just going to be this dimension right here. And for B, that's going to be, let's see, I'll use a different color here. This little green, I never use him. It's going to be this direction right there, dimension right there. And then because I know the velocity of B, I can find the omega by taking that dimension that I just found up here and dividing the velocity by it. So now I've found what my omega ABC has to be. And I didn't have to find the velocity of A. It was not required. But if I wanted it now, I just have to multiply this value times 1.69, and I would get the velocity. And then I'm able to find the position of C with respect to ICR, and I kind of made it look a little easier than it might have been. It might not be quite obvious first when you start to look at this, so you might want to pick that apart. And I'm able to add these two together right here and down here, and then have this guy right here. So I'm able to find that dimension. And now I can find what the velocity is at C right here by way of just taking that omega that I found and multiplying it by that distance. It wasn't asked for, like I mentioned, but you could find the velocity of A easily. The angle is a little bit more difficult, but once we had this geometry up here, this velocity of C is what we want to try to get, and we would see that that it's going to be by the way, we're going to see that that's actually going to be the same angle right here as this velocity right in here, because you have to work through those dimensions. But you would see that the rise over the run of this being the rise in this case, because it's opposite from the angle that we want, and the run is just that adjacent side, and I get 74.3. So we get the same answer, which is it's a pretty easy thing to do in many cases, but it's always the geometry that makes ICR a little annoying.